All right. Hi, everyone. We're going to get started with our lesson 6, conservation of matter. I know we did touch on this a little bit in class before we left. This is going to be a pretty general review, just making sure that we have those main concepts down. But of course, before we get started, our do nows. So for do now number 1, Isabel wants to surprise her family and make breakfast. She cuts up strawberries, bananas, and blueberries, mixes them together to make a salad. Is this salad a result of a physical or chemical change, and why? Next, do now number 2. Next, she mixes eggs, flour, milk, and sugar and makes pancakes. Are the pancakes a result of a physical or chemical change, and why? All right, let's go over our do nows. So for number 1, mixing fruits into a salad results in a physical change. Even though we called that mixture something new, for example, a salad, the original components are still there. The strawberries, the banana, everything was still there. Molecules were not changed and nothing new was created. So even though we're no longer calling it bananas and strawberries, we're calling it a salad, just because it has a new name doesn't mean that it's a new substance. Do now number 2. Making pancakes results in a chemical change. Most of us usually get this right. There are a couple of students that sometimes get confused because they're only thinking about the batter. They're thinking about the milk, the eggs, the sugar, the flour. They're thinking of that as a mixture, but not thinking about it all the way till the end where it gets cooked. So especially because it gets cooked, we know that this is a chemical change. We cannot get our original components back. I want us to look at this picture. We have a picture of a cake in the oven. I want you to take a really quick second and observe what's happening. Now go ahead and answer in the box that pops up to the right. What do you see happening to the cake? Be sure to describe what you see in terms of the size, shape, etc. All right. So before we get started, let's just really quickly go over matter. We've talked about matters pretty much since day 1. We know that everything that we see around us is made of matter. The computer that you're looking at, the phone that you might be looking at, the bed that you're sitting in, the chair that you're sitting at, everything is made of matter. The smallest building block of matter, so the smallest piece of matter that you can get is an atom. Right? We know that an atom is the smallest building block of matter. You need more than one atom to create molecules. Molecules create everything else. We also know that matter exists in 3 main states: solids, liquids, and gases. Now, about those states, we know that they can change from one to another. For example, if you take a pot, fill it up with liquid water, and you turn up the heat, what phase change will you see? We will see evaporation. That liquid water is turning into a gas, and once that gas is formed, even though we can kind of see it here, eventually we will not be able to see it. It looks as if it disappears. When matter changes drastically like that, it's not actually created or destroyed. The law of conservation of matter tells us, actually, hold up, let's just say it really quick. Say law of conservation of matter. So conservation of matter, that's what we're talking about. The law of conservation of matter tells us that all of the atoms that were there before the change, whether it's physical or chemical, will be there after the change. Very quickly, let's focus on this word, atoms. Say atoms. All of the atoms that were there before the change will be there after. We're not saying molecules, we're not saying substance, we're specifically talking about the atoms. For example, here we have liquid water that was changed and turned into water vapor, just like that example that we saw. We have 1, 2, 3, 4, 5, 6 oxygen atoms, or the red ones, and after the change, we still have 1, 2, 3, 4, 5, 6 atoms of oxygen. It looks like if it disappears, but it doesn't, right? So how do we know that it doesn't disappear? Aliens. Just kidding. We can observe if the number of atoms before and after a chemical change remain the same by taking the mass of the substances before the change and again after. This is because we can't actually go into each substance and count the atoms. It's impossible. Even if we had some sort of crazy microscope that could do that, there's way too many. So in order to kind of do this more quickly, we take the mass. In order to prove that matter was conserved, essentially that matter was not created and that matter was not destroyed, the masses must be the same. They must be equal. So to kind of look at what that might look like, we're going to watch a very quick video of these students making a mixture. Now, I'm just going to give you total honesty. When I practice doing this video, sometimes these videos click out. So I might be playing it and then it'll go to the next slide. So just be patient. I might have to come back and reset it a little bit. So let's see what's happening in this video. We have a student here measuring out sugar. We can see they have 25 grams of sugar. This other student is measuring out water, and we see that they have 150 grams of water. So what they're going to do is they're going to pour that sugar into that water. Now she's going to mix it. So as she's mixing it, we see something happen. See, he's very concerned. We see something happening in this beaker. Can you still see the sugar? What do you think happened to the sugar? So it looks like it disappears, right? But we know for a fact that that's not true. The law of conservation of matter tells us that we cannot create or destroy matter. So how can we prove that that sugar is still there? Well, we're going to weigh it. So if the sugar disappeared, we'll only have the mass of the water, which was 150. But if the sugar is still there, then it should weigh 175. And we can see, what did I tell you guys? This thing was going to do that. And we can see that at the end, when she weighs it, we actually have 175, which is the mass of the water and the sugar combined. Can you think of another way that we can prove that the sugar was still there? Well, we can try separating it. We can try separating it by its properties. Now, the property of the sugar is that the sugar, even though we can't see it, is still a solid. The mixing and the dissolving help the particles become small enough for us not to see them, but the sugar is still there and the sugar is still a solid. So what we can actually do, oops, I told y'all I was going to do this to me. What we can actually do is evaporate the water. The water is a liquid, so you can evaporate it out. And when you do that, you can see that you still have the solid sugar there in the pan. So this is a way of proving that we did not destroy matter, even though it appears to have disappeared. Let's go ahead and look at another example. We're going to do an experiment here where we're combining vinegar and baking soda. So really quick, looking at the balance, what is the mass of both substances? All right, so what we're going to do now is we're going to combine them. I'm going to take the vinegar and pour it. What do you see happening to the vinegar? Is this a physical or chemical change? Look at the mass. The mass is now 34.2. The initial mass, if you remember, was 35. Was matter conserved? Why or why not? So it looks like matter was not conserved. We started with 35 grams and we ended up with 34.2. So what happened to that missing 0.8 grams of matter? Well, as you saw, this mixture began to bubble. It started fizzing. And we know that bubbles are full of gas. So what ended up happening was that during that chemical reaction, 0.8 grams of air or gas was released. Can you think of a way to Oh, we already answered that. Can you think of a way that we can change the experiment to see if that's actually what happened, if gas was really created? Think of a way that you can change this experiment to capture those atoms. So one of the things that we can do is cover it with a balloon. I'm going to try to pause it. So what we have here is we have a beaker that is covered with a balloon. Now the balloon creates a tight seal at the top. So anything that gets created will not be able to escape unless the balloon is taken off. Now what we can't really see is that inside the balloon is baking soda. We already know that in the beaker is vinegar. So we have vinegar, we have the baking soda. What is the mass of this? Oh, I already showed you, sorry. It was 142. So we mixed the baking soda and the vinegar. Basically, they just pulled up that balloon. So it's a physical or a chemical change. So water, carbon dioxide, and all of that was produced, which shows that it was a chemical change. This is going way too fast, which shows that it's a chemical change. The mass after the reaction was 142 grams. Is this mass the same as it was before? Yep, we started over here with 142 grams. Let me see if I can bring it over. We started with 142 grams and we ended with 142 grams. That means that when we put that balloon on, it created a seal that actually trapped the gases. Because we were able to trap the gases, we were able to take their mass. So sorry that that video was all over the place. It went by really, really fast. Okay. So up until now, we've been seeing experiments where it looks like matter is destroyed. It looks like matter disappears. This experiment that we're going to see now is actually going to do the opposite. And we'll see why in just a second. Okay, I'm going to do my best to control this video. So we have sand, and he was covering it with really, really, really flammable substances. It was a liquid that's very flammable. Now here we have 20 grams of sugar, and we have 5 grams of baking soda. What they're going to do is they're going to pour the baking soda into the sugar, and they're going to mix it up to create a mixture. When they mix the baking soda and the sugar, is that a physical or a chemical change? All right. So she's taking the mass of both of them. She doesn't show you, but it's 25 grams. Now they put this mixture on top of the sand and the lighter fluid. They're going to light it up with some fire and watch what happens. What is happening to the baking soda and the sugar? How is it changing? Well, it looks like it got bigger, right? It looks like it's much, much bigger than that mixture. No, sorry, you guys. Than the mixture that was in that really, really small bowl. So let's go ahead and bring it over here. Right, so it looks way, way bigger than when it was just a powder on top of the sand. So what they're going to do now is she's going to eventually, right, see how much bigger it is? Remember, it was just that little tiny pile of the white powder. So his helper is going to go ahead and take this new formation, and she's going to take the mass. The mass was, sorry, y'all, the mass was 23 grams. We know that they started off with 25 grams of sugar and baking soda. What happened to the missing 2 grams? So basically, that those missing 2 grams were gas that was lost during the reaction. But in this case, what was happening is that as the gas was being created, it was expanding the matter. It was making it look like it was bigger. If you saw, right, the size of that pile of the white powder before and compared it to the size of that really large they call it a sugar snake, that was created, it looks much, much bigger. It looks like if we added more matter. And that's not actually true. The formation of the carbon dioxide made this expand and made it look bigger. In fact, this actually weighs less than what both of those powders combined weighed, right? Those combined were 25 and this was 22. It was simply the making of those bubbles, the releasing of that carbon dioxide, that made this grow and appear bigger. All right, so let's get our NanoVision goggles on. So when we're talking about NanoVision, we want to talk about what this looks like at the molecular level. Remember, conservation of matter talks about keeping the same number of atoms, not molecules. We're interested in the number of atoms. So here we have these two molecules, right? Molecule 1, molecule 2, and they're going to go ahead and react. We see that these, right, this atom broke off, and these broke off. This is a chemical reaction. Let's go ahead and count the atoms that we start with. This is the end, so let's go ahead and let this start over. We see that we have 3 gray atoms, 6 white atoms, 1 bluish atom, and 2 purple. Let's see what we end up with afterwards. So this is right as it's about to change. All right, and we end with, we still have 3 gray atoms, 6 white atoms, 1 blue atom, and 2 purple atoms. The number of atoms stayed the same, even though we ended up with different molecules, right? This molecule is not going to exist after the change. As you can see, boom, it turns into a new molecule. But the molecules is not what we're interested in. We're interested in whether or not the same number of atoms were there. And we can see that the number of atoms stayed the same, even though we ended up with different molecules. So now it's your turn. Jaylene has 16 grams of chocolate milk powder and pours out 124 grams of milk. She then mixes the powder in the milk. If her mixture shows conservation of matter, how much should the mass of her mixture be? Well, we know that we're going to need to add both of them. So we have 124 grams of milk, 16 grams of that chocolate powder, and that is going to give us 140, don't forget your units, y'all, grams. So in order to show conservation of matter, that mixture needs to be 140 grams. It was, so we know that matter, or mass in this case, was conserved. Now let's think of a different example. What can happen during a change that might not show the same mass of a mixture after a reaction? So let's say that you have 30 grams of two substances, you mix them and you end up with 16 grams. What might have happened? There's a lot of different things that could actually have happened. Some of these that we don't actually think about all the time, but it's very important to keep in mind when we're doing labs, is human error. Maybe when you were mixing, you dropped a couple of grains of whatever your substance was. You dropped a couple of drops of it. In those grains and in those drops of liquids are millions of atoms, right? You're losing mass. The other and most common thing is that you're creating a gas. Maybe you had that much gas escape from your reaction, which lowered the final mass. It doesn't mean that you destroyed matter. It just means that matter escaped from the container that you are taking the mass in. Right? Changes in the phase of matter. Whenever a gas is formed, atoms escape into the air, and all atoms have mass. So let's go ahead and recap, which means it is time for our major keys. Major key number 1. Matter can be defined as any substance that has mass and takes up space. Remember, taking up space means that it has volume. Atoms are the smallest building blocks of matter. Major key number 2. The law of conservation of matter tells us that matter can neither be created nor destroyed. All the matter that is there before the change will be there after. You cannot make more and you cannot destroy any of it. Major key number 3. Conservation of mass can be proven by weighing the substances before and after the changes. And we know that in order to prove conservation of matter, the masses must be equal. Even if there's a chemical change and the molecules are different, the masses need to be the same. The number of atoms need to be equal. And major key number 4. When matter seems to appear or disappear, it is due to change in phases. It is not magic. It's not actually appearing or disappearing. It is simply becoming something new. It's making it look bigger, or it's making it look as though it disappears. So let's go back to our cake. Is this cake getting bigger because it's getting more matter? Go ahead and change your answer now in the box. So we know that this cake is not actually adding more matter to it. It's not actually getting bigger because we're creating more matter. There are bubbles that are forming within the cake that are forcing the cake to rise up and increase in size, very much like that sugar snake that we saw earlier in the experiment. And that's it. Again, make sure you watch this video until the end so that your answers get automatically submitted. Go ahead and log into Illuminate to take the Conservation of Matter exit ticket. Please make sure that you are looking at our weekly dashboard. I did put a survey that I would love for you to take. I swear it is 100% anonymous. I just want to know, kind of like how I'm doing, what it is about remote learning that you like, what's something that you feel that we can change. And if you have any questions, as always, y'all know where to reach me. Hope you have a great rest of your day.